We all are aware of the three states of matter: gas, liquids, and solid. These three states differ significantly from one another on the basis of molecular arrangement. Solids have a regular structure, liquids a semi organized structure, and gases have almost no structure at all. In this session, we will talk about the rate of thermal expansion in each state of matter. We already know that when we heat any state of matter, its temperature increases and internal energy rises. Another consequence of heating a state of matter is that it thermally expands. Though the rate of expansion varies significantly between the states of matter, but they do expand and contract when heated and cooled respectively. But what is thermal expansion? Let's try to understand thermal expansion with the help of an analogy. In the beautiful plains of physics land, you see a monster playing music with its radio. At first, it seems harmless, but you soon realize that it's not just any music. It's the music of horror from the disease we all know as BTS. The terrible music forces Billy to transform into Shazam to deal with this threat. Moreover, it forces nearby Pokemon to evolve into their ultimate forms to silence this monstrosity once and for all. However, we are more concerned with something else. As Billy and other Pokemon evolve to purge the world of BTS, something interesting has happened. They occupy more volume now than before. In context of physics, the music is akin to heat energy provided to the substance and the transformation through which Billy and Pokemon undergo to increase the space they occupy is known as thermal expansion. In order to understand thermal expansion, we first need to briefly discuss the atomic structure of substances. We know that all solids are made up of atoms that are arranged in a regular pattern as seen in the image. Let's dissect this pattern to obtain a single layer of atoms, and within that single layer, let's isolate a single row of atoms. These atoms are currently stationary, which is only possible at absolute zero temperature. Normally, these atoms are in state of constant vibration. They can move vertically along the direction of y-axis, horizontally along the direction of x-axis, or perpendicularly to the direction of both x and y-axis along the direction of z-axis. Let's consider the first atom in isolation. It moves in a vertical direction, upwards and downwards along the direction of y-axis, perpendicular to both x and z-axis. In reality, at a given time, more than one atoms move along the vertical direction, depending upon the intensity of the heat source. To visualize their direction, think of them as if they are moving upwards and downwards on your laptop screen. Some atoms also move along the direction of z-axis. They move perpendicularly to both y and x-axis. To visualize their direction, think of them as if they are moving in and out of your laptop screen, just like 3D movies in cinema. Atoms also move along the direction of x-axis. They move perpendicularly to both y and z-axis. To visualize their direction, think of them as if they are moving in a forward and backward direction on your laptop screen. When heated, these molecules start to vibrate more vigorously within the structure. As they move more vigorously, they start to occupy more space within the molecular structure. As a result, the volume occupied initially by the small number of atoms increases. The bonds holding the structure together still exist, so the state is still solid. If heated beyond a certain point, these bonds start to break and the substance undergoes phase change. So, if a regular solid is heated, its length increases along the x axis, height along the y-axis, and width along the z-axis. This phenomenon is known as thermal expansion. When an iron rod is placed over a fire, it turns red. This shows that molecules in iron rod absorb heat energy and they start to vibrate more about their mean position. When they absorb sufficient kinetic energy, they start to move even further away from each other. This means the volume of the substance has increased. This is thermal expansion. The bonds are still present, so the substance hasn't undergone change of state. Consider a red hot metallic sphere placed over a ring. When the ball was heated, the atoms start to vibrate more vigorously and eventually moved away from each other. As they occupy greater space than before, we say the substance has undergone thermal expansion. Note, the size of the atoms remain constant. it is wrong to say that the size of atoms has increased. In reality, only the space they occupy has increased because of the greater movement. Moreover, the bonds holding the molecules are still present, so the substance hasn't undergone change of state. Now, if we cool this red hot metallic sphere by placing it in a beaker of water, we can see that the metallic sphere can easily pass through the ring, which was not possible when it was red hot. What has happened? The energetic molecules in the red hot metal sphere lose their energy to the water molecules and are pulled back closer by the bonds holding the structure together. This is known as thermal contraction. Suppose you have a flat bottomed empty flask fitted with a cork and capillary tube. As you fill it with water, it acquires the shape of the container. It is filled up to a height P on the capillary tube. The flask is then placed in a metal container which is later filled with boiling water. Observe carefully the level of water in the capillary tube as the temperature increases. Initially, the water level will fall to a level Q, and after some time, the water level will start rising. It not only reached P, but also moved further up to R. What has happened? When we poured the hot water, the flask absorbed heat and expanded slightly. Water takes some time to transfer heat within the flask as it is a bad conductor of heat. So the water level initially falls from P to Q. After some time, the liquid in the flask starts gaining heat. The liquid starts to expand and hence it rises within the capillary tube to a level R. In most examination questions, you can ignore the expansion of container unless specifically stated. Different liquids expand by different amounts. Take two identical flasks containing water and alcohol such that their level is the same. Place these two flasks in a large container and pour water in it. Now heat the water until it boils. Sometimes later, you will observe that the level of alcohol rises more than water. This shows that upon application of same heat, alcohol expands more than water. The diagram shows gas molecules held at 200 Kelvin temperature. We can see that these molecules move at random and have no intramolecular forces to hold them in place. As a result, they move freely and collide with the walls of the container. These are characteristic properties of a gaseous state. Now, as the temperature of gas rises gradually, we see molecules start to move with increasing speed, resulting in more collisions among themselves and with the walls of the container. At 2000 Kelvin, the molecules are moving with greatest kinetic energy and highest speed. So, just like solids and liquids, molecules in gases also move at higher speeds when exposed to high temperature. This effectively means that thermal expansion also occurs in gases. We all are aware of the three states of matter: gas, liquids, and solids. The three states differ from one another on the basis of molecular arrangement, which in turn is dependent upon the strength of bonds in each state. The stronger the bonds, the more it is unlikely that the molecules can move freely when heated. Therefore, the rate of thermal expansion is inversely linked to the strength of bonds in each state. As we move from gases to solid, the strength of bonds increases. Therefore, the rate of thermal expansion decreases. In other words, the rate of thermal expansion rises as we move from solids to gases.